Hello, everybody. My name is Alex.
I'm Christian.
I'm Matthew.
I'm Jungho.
And I'm Carmen.
And today we're going to be going through some research in order to answer the question of how does El Nino affect ozone concentrations? So first things first, we're going to introduce El Nino. What is El Nino? El Nino is a weather pattern that occurs over the Pacific Ocean, and it is the unusual warming of surface waters in the Eastern Pacific. Now, how does this form? So during normal conditions, trade winds blow from east to west, pushing warm surface waters towards Asia, piling it up in the Western Pacific. In some years, though, the trade winds weaken, the warm surface water moves eastward and reduces the upwelling of cold water off the coast of South America. And climatologists call this El Nino. Now, how does tracking work? Tracking requires an array of satellites and buoys that gather data regarding ocean temperature, wind speed, and direction. More specifically, satellites measure the heights of sea surface and serve as a transmitter for buoys out at sea, while buoys arranged along the equator measure wind, shortwave radiation, rainfall, air temperature, relative humidity, sea surface temperature and conductivity, and subsurface temperature, conductivity, and pressure. With this information, the climatologists can piece together a probabilistic forecast months into the future. La Niña follows El Nino, where eventually the trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back to the Western Pacific and restart the upwelling of cold water into the surface in the Eastern Pacific. These strong trade winds are a signature of what is called La Niña, which brings unusually cold conditions in the tropical Pacific. La Niña could lead to drought in the southern US and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. Now, how often does this happen?
So El Nino events have been occurring for thousands of years. These events occur every 2 to 7 years and typically last 9 to 12 months and usually starts in December. The last El Nino to occur was last year, which will be talked about later. El Nino can cause amplified wet conditions in one area and dry conditions in another. Because of this, businesses like fishing can plummet due to the upwelling being limited. Also, in drier areas, rain-driven agriculture can decrease, causing a shortage of food, and the occurrence of diseases such as malaria can increase due to more extreme conditions. The amount of storms can increase, while in other areas, the amount of wildfires can increase, which could cause economic damage. And next, we'll discuss the locations affected by El Nino.
Countries in Eastern and Southern Africa and the Pacific Islands, Southeast Asia, and Central America are most at risk from El Nino. El Nino impacts Earth's climate differently depending on what time of the year it is, based on how warm the ocean water is. It is capable of affecting weather patterns across the world, bringing rainy weather to the normally dry areas and plunge normally wet areas into a long-term drought. El Nino can even influence hurricane season.
The most recent event lasted 11 months during September of 2018 to August of 2019. The left figure measures the monthly sea surface temperature of Niño 3.4 index, which is visualized on the right. The purple line represents the trend line of difference from average temperature, showing the difference increase at September of 2018 and coming back down past the El Nino threshold at August of 2019. As of June 1st, 2020, neutral El Nino conditions are present. According to the World Meteorological Organization, as of May 2020, there is a 60% chance that neutral conditions will continue into summer of 2020. There's a 10% chance of El Nino event happening and a 30% chance of La Nina event happening. The weekly sea surface temperature anomalies on the right supports the 60% chance of neutral conditions because of the decreasing temperature of the Pacific.
So next up, we're going to be talking about ozone. So what is ozone? Ozone is a highly reactive gas that consists of 3 oxygen atoms that can be made by us and the stratosphere. There are 2 different kinds of ozone, the stratospheric, or what we call the good ozone, and the tropospheric, or also known as bad ozone. It can be seen on the graph how the stratosphere has more ozone than the troposphere does, since the stratosphere naturally makes the good ozone through the interaction of solar ultraviolet radiation with molecular oxygen.
Okay, so first let's talk about stratospheric ozone and how is it formed. So stratospheric ozone is formed by chemical reactions involving solar radiation and oxygen molecules. The oxygen molecules absorb incoming UV radiation from the sun, which allows them to break apart into 2 free radical oxygen atoms. Each of those free radical oxygen atoms are then able to react with a separate oxygen molecule to form the triatomic oxygen molecule that we know as ozone.
Think of it this way, where this ozone layer acts like a giant filter between the sun and Earth. This ends up reducing the amount of exposure to UV radiation that can cause skin cancer and cataracts.
So now that we've discussed stratospheric ozone, let's talk a little bit about tropospheric ozone. So tropospheric ozone is formed by a similar mechanism to that of stratospheric ozone, except this time we're going to involve NOx species. So tropospheric ozone formation occurs when nitrogen oxides react with oxygen molecules in the presence of sunlight. And there's an exchange, as shown in the diagram, between the oxygen atom and the NOx species. One thing that's important to note, though, is that this cycle between NOx species and molecular oxygen is frequently disrupted by volatile organic compounds, also known as VOCs, which leads to a buildup of ozone in the troposphere. This is why NOx species and VOCs are often called ozone precursors. They are lead players that contribute to the formation of tropospheric ozone.
As we know, tropospheric ozone is formed from vehicle exhaust, industrial emissions, and other processes that releases volatile organic compounds and nitrogen oxides that gets heated from the sun. Therefore, this creates smogs that reacts chemically with many biological molecules in the respiratory tract, which then leads to a number of adverse health effects.
All right, so now that we know a little bit about ozone, let's talk about how this looks like from space. So here on the left, I've included 4 images of Earth from NASA's Goddard Space Flight Center. So these graphs show us the latest status of the stratospheric ozone layer over the Antarctic. So these, as you can see, are recent images dating from May 23rd to May 29th of the year 2020. The blue colors show where there's less ozone, and the green colors show where there is more ozone. So what these satellite instruments show us is that there's a seasonal hole in the ozone layer over the Arctic pole. And this can also be confirmed on the right with the graph. This graph shows a correlation between the area of the ozone hole to the minimum amount of ozone throughout the year 2019. So again, this is all recent data you can find on NASA's website. So ozone, being a very active chemical, plays a significant role in the physical and chemical properties of our atmosphere today. So through this research project, we decided to study exactly that, how recurring weather patterns such as El Niño can impact ozone in our atmosphere.
There is still a lot of research to be done on the connection between El Niño and ozone. However, scientists have found interesting connections around the world and in the US. Globally, research in the UK found that the northern hemisphere has an increased concentration of ozone, while the southern hemisphere has a decreased concentration of ozone, with a slight decrease overall. In the figure, the red line marks the El Niño cycles, and the blue and purple lines represent the difference in ozone between fixed meteorology and fixed fire emissions, respectively. These indicate that there is a decrease in the ozone concentration that stays relatively constant throughout the years. In the US, researchers at Harvard University proposed that El Niño increases ozone concentration by 1 to 2 parts per billion in the northeastern states and decreases ozone concentration by 0.5 to 2 parts per billion in the southeastern states. This is illustrated in the figure that maps the ozone concentration difference in parts per billion during the El Niño between 1980 and 2016. Red indicates an increase of ozone, blue indicates a decrease of ozone, and the white is where the ozone does not change from El Niño to non-El Niño year. El Niño can influence tropical ozone through many mechanisms. A team at Beijing Normal University reveals anomalous propagation and dissipation of planetary waves at mid-latitudes and a lead-lag correlation, with significant correlations with tropical and high-latitude stratospheric ozone, where El Niño leads ozone by 3 months. Antarctic stratospheric ozone does not impact El Niño, whereas Arctic stratospheric ozone does, as shown in the figure. Another team at NASA Goddard Space Flight Center and the Jet Propulsion Laboratory studied the 1997 to 1998 El Niño season, and they discovered that ozone is affected by large-scale circulation processes associated with the shift in the tropical convection pattern and events such as forest fires.
Under normal conditions, the ozone layer in the stratosphere is thickest at the equator and thinnest at the poles. This is due to ozone being produced by photochemical reactions, and there's more sunlight directed at the equator compared to the poles. These concentrations also vary depending on seasons and geography. For example, during the spring, there is an increased density of stratospheric ozone in the polar latitudes of the northern hemisphere, while in the southern hemisphere, the highest density is at the mid-latitudes, which is shown in the figure. The reason for ozone concentrations being highest at these latitudes is due to atmospheric circulation during the spring, which transports ozone from the equator to these latitudes. There's also a dramatic decrease in ozone over Antarctica due to the unique conditions in polar stratospheric clouds, which we learned in class. For tropospheric ozone concentrations, trace gases such as nitric oxide, carbon monoxide, and organic compounds, which are emitted from anthropogenic sources, cause the formation of ozone through photochemical reactions. Since most ozone comes from anthropogenic sources, areas like oceans have low ozone concentrations, while industrialized areas have high tropospheric ozone concentrations, especially during the summer. Overall, every year there are increases of tropospheric ozone due to the increasing use of fossil fuels.
So during El Niño conditions, how does El Niño affect the concentration of ozone in the atmosphere? Well, ozone varies through seasons and responds to weather variability even during erratic weather patterns caused by El Niño. However, we can point out the average pattern of ozone in the figure below, which shows the global mean volume mixing ratio of ozone from 1993 until 2001. Because the strongest El Niño event ever recorded in history happened then between 1997 to 1998, this information is important in understanding the ways ozone responds to El Niño conditions. The impact that El Niño can have on ozone considers the following details: red being the highest concentration in the northern hemisphere and blue being the lowest in the southern hemisphere. Thank you for listening. Any questions?